hypercontractivity in the group demo 2 to the n is a part of a subfield of additive combinatorics called analysis of Boolean functions, and it has a lot of applications to theoretical computer science, to calculation, to social choice, and the external combinatorics. And what I'd like to talk to you about today is how hypercontractivity and representation theory how they combine together to yield result in non-abelian additive combinatorics. And if I have time, I'll also talk about how can hypercontractivity be used to give results in representation theory, character theory. Okay, so let's say that we have a group G. A subset of G is said to be product free. If for all A, B, and A, B is not in A. In 1985, Baba and Shosh posed the following problem. Given a group G, what is the largest product-free subset of G? Then they suggested the alternating group. Of even permutations as the first case to consider. And there were several works. So first there was the work by Gowers, and then by Sean Eberhard, and then with Peter Kivash and Dor Mintzer. We solved it for insufficiently large. Today, I want to talk about this result. I will mainly talk about the result for compactly groups or for groups of matrices in general.
So what was the result that you got?
So we completely determined the largest product set. So it's a specific example. So it's the set of permutation that's in a given element X to a set I, but also send set I to its complement. So the sum X in N.
How large is this?
Roughly 1/√n in terms of density. And
For what size of I, sorry?
I is roughly √n in terms of it's like a birthday paradox thing. The probability that I is sent to its complement is constant. So let me tell you first about the Gauss work. So Gauss introduced the following definition. That the group G is quasi-random if for all representations from the group that are of dimension at most d-1, the representation must be always the identity. Okay, so every irreducible representation must have dimension at least. And what Gauss proved, the more general statement that if G is equally random, then every product presets its density smaller than d to the minus 1/3. And then Nikolov and Pieber they realized that all the results about word maps, images of word maps that group theorists were interested in resolved using representation theory, they are actually a corollary result. And basically, they show that if A has size at least b to the minus 1/3 times the size of the group, and G is t quasi random, then A cubed is equal to G. And so that's for finite groups. But then you can ask the same thing for compact Lie groups, or for compact groups in general. And so he asked basically the same thing. So we asked it for the special unitary group. So the set of unitary matrices of determinant 1. And yes, what's the largest product-free subset of G? For a product-free set A, where mu is the probability Haar measure. So for compact groups, there is a unique measure that's unique probability measure that's invariant from the left and is also invariant from the right. And he asked this question that makes sense for compact groups in general. And basically, we have an action of SUN on the sphere S2n minus 1. And you can take all the elements, send the south pole close to the north pole. So you can take a set of matrices A such that A of E1 is close to minus E of 1. And because unitary matrices preserve distances, if you take two matrices that send E1 close to minus E1, the product is going to send E1 close to E1, and therefore this set is product free. So this set is product free. And it's of measure e to a constant times n.
Like e to the negative of that.
Yes, so thank you. Yeah, so e to the minus constant times n. On the other hand, the group SUN is only n quasi-random. To have a representation of dimension n just by sending every matrix to itself, and that's the minimal dimension of an irreducible representation. So Gauer's bound is only n to the minus 1/3. This leaves an exponential gap between what the representation theoretic methods can do and what our example gives. It turns out that this problem was posed from an entirely different direction by physicists, that they cared about quantum communication protocols. So basically, they had an efficient quantum communication protocol, and they were interested in showing that all the classical communication protocols that try to achieve the same task would have to be much less efficient. And they came up with the following conjecture. So, okay, so what the conjecture is the following, and the conjecture is sharp because in some senses it's stronger than Gauss conjecture in the qualitative sense, and quantitatively it's weaker, but it is sharp. So suppose that you have sets A, B, and C of a measure at least e to the c n to the minus e to the minus c n to the 1/3. Then when you choose randomly random element A, so if you want to choose it from the Haar measure and you condition that this element is in A, and then you choose a random element from B, then even if you have these very small sets A and B, the product is uniformly distributed in a very strong sense. So the probability that AB belongs to C is very close to the Haar measure of C. So it's in particular, this implies that product free sets must have measured at most e to the minus c n to the 1/3. Because if you take a product free set, the probability that if you choose randomly two elements from A, probability the product is in A is 0. So it's not very close to the measure of the set. And here this e to the minus c n to the 1/3 is sharp. And you can also get mixing time results. That if A and B are sets of measure e to the minus c n to the 1/2, then the product is close to the uniform distribution and the total variation distance.
What are the examples? The example of size. There are examples of size e to the minus c to the n to the 1/3 where you don't have this product mixing thing. So what
Yeah.
happens for those?
What do you mean? What happens for those?
As in, is it too small or too large?
You have a set. You have 3 sets of measure e to the minus c to the times n 1/3 that this doesn't hold. And the probability is too small. Yeah.
And on that board, theta of n is just approximately n, constant times n.
Yeah.
You're saying that like this conjecture is sharp, but But like
For the product free sets, it should be e to the minus a constant times n, but for the product mixing, where you have this probabilistic thing, then yeah, then this is sharp.
Is it the same kind of set where you take balls around the North and South Pole? Like,
Yeah, everything. The examples are always the obvious examples. Yeah.
it's like conjecture to be sharp. We haven't proven that it's sharp, right?
Um,
not stated that it's true.
okay. So yeah. Okay, so the theorem by Alice Kinlan. Minter. Our theorem is that the product mixing conjecture is true. And this is based on hypercontractivity. We'll tell you what it's about. Are there any questions before I move on?
So the product mixing conjecture, is that conjecture?
Yeah. So this statement is true. The one way to prove the results of Gowers is using the Sarnak-Shmuel lemma. Evolution functions on a group is the expectation of f of y, gy inverse of x. And what they proved in the context of the spectral theory of automorphic forms is that if f and g are functions yeah, let's say they're in L2 of G, and G is the quasi-random. Then if you take the convolution of f and g, it's very close to the product of the expectations. So the two norm of that, at most, the two norm of f times the two norm of g divided by root d. So this means that here you have an expectation of the product of two random variables, f of y and gy inverse of x. And these variables are very much dependent on each other. The product of y and y inverse x is always x. But even though they are dependent, they behave like independent random variables. And the convolution is close to the product of the expectations. And that sort of explains the name quasi-randomness. but it also has a relation to quasi-random graphs.
Bowers introduced this notion of quasi-randomness for groups, so I'm confused why this result from 1991.
Yeah, so they just didn't call it the quasi-random, but they proved this result, and they proved it in a slightly different context. So it's not about functions on a group, it's a finite group acting on some compact space, and then basically, yeah, okay. And it turns out that you can rephrase this product mixing result analytically by saying that, so let's say that you have A, B, and C of measure least e to the minus C and to the 1/3. And if you now write F to be the indicator of A divided by the measure of A, and also do the same for B and C, then it's about showing that F convolution G inner product with age. It's about showing that this is close to the product of the expectation. Show that this is equivalent to factor of 1.1. And yeah, and basically using this, you can get something for sets of measure not at least n to the 1/3, because you can show that F convolution G is close to the product of the expectations. So the inner product is close to the product of all the expectations. So this would work only for subsets of measure at least n to the minus 1/3. Okay, so how do you go beyond this quasi-randomness parameter? So what we do is use ideas from analysis of Boolean functions. And there you have the KKL theorem, and maybe BKS, Benjamin Nikolai Schramm also deserve credit for this. So that's a theorem called the level D inequality. It says that if you have a function on the Boolean cube, say 2, 0, 1, and the expectation is some alpha that's at most 1/2. Then you can say something about the Fourier spectrum of this function. Okay, so you can show that maybe just say that a function on the Boolean cube can be written, can be expressed according to its Fourier expansion, and the characters are indexed by subset, and chi of S is the product over I and S of xi. And what the theorem says is that if you take the sum of all sets of size D of the square of the Fourier coefficients, then this thing is small. This is at most alpha squared up to logarithmic factors. So here we're thinking about think of f as being the indicator of some small set A, and then this alpha parameter is very small, and you always have a bound on the sum of the squares of the Fourier coefficient that's at most alpha, but you can actually get something much closer to alpha squared up to these logarithmic factors. That's the theorem. And usually in additive combinatorics, you don't care about the size of the sets somehow, because it's something related to a choice of basis. But it turns out that this is a non-abelian phenomenon that's related to the action of the symmetric group, or more precisely, a semi-direct product of the symmetric group with the cube. So this group acts on the space of Boolean function. It acts on the cube. Cosimo 2 to the n acts by translation, and Sn acts by commuting the coordinates. And this action of the semi-direct product yields a decomposition of the space of Boolean functions into n parts. And this part is actually the projection, it's the L2 norm of the projection of F onto the irreducible representation. So it turns out that the space, you can define a space V equal to D, which is the span of all the characters of level D. And this, and the decomposition of the group of Boolean, the composition of the space of Boolean functions, or functions on the cube as the sum of the spaces V equal to D. This is exactly the decomposition of the space into some irreducible representations. So this is actually a non-abelian theorem, even though it looks like an abelian one. Okay. And how you should think about this theorem is that the Fourier spectrum indicators of small sets is concentrated on the high degrees. But also the high degrees correspond to high dimensional representation.
This would still be true, right? If you applied a random linear transformation to f2 to the n, and then wouldn't that send your low degree ones to high degree ones?
Yeah, if you do that, you would get chunks lemma when you apply with d equal to 1.
Not vice versa. I doesn't necessarily transfer to low.
Oh, no, but which ones are high and which ones are low are not preserved.
So you could do that, and it's useful. Like with d equal to 1, it's chunks lemma, which is useful. So, yeah. But I don't know if it's useful for other values of d. Okay, so if you look back at this Sarnak-Schwell lemma, you see that you have this root of d in the denominator, which means that the low dimensional representations are what we are trying to avoid. If we only had high dimensional representation, we'd get better bound here. And sort of the idea is to show that the phenomenon, like in the Boolean cube, that all the Fourier spectrum is concentrated on the high dimensional representation. But this thing holds also for the special unitary group. And that's what we did. So you can define a space D at most D in SUN to be the space of degree at most D polynomial. In the entries of the matrix. So, for example, if you take the real part of A11 squared plus the imaginary part of, I don't know, A12 squared, this would be like a polynomial of degree. We can define the space of polynomials of degree at most D, and then what you can do to get you can also define the space V equal to D, just to take the intersection of the space of the polynomials of degree at most D with the orthogonal complement of the polynomials of degree at most D minus 1. Okay. And then what we proved is that you have an analog of the KKL theorem. So suppose that F is now a function from x to n to 0, 1. Expectation alpha at most 1/2. And for some reason we need it to be at least the minus root n. Important. And then you get that if you project this function f to the space V equal to D and take the L2 norm of that, then this is at most alpha squared times log the D of 1 over alpha. So you get exactly the same statement for function the unitary group.
So I have a question. So hypercontractivity is often stated as an LP improving property of the noise operator.
Yeah.
Is that related to this?
This statement follows from hypercontractivity on the Boolean cube for the noise operator.
Right.
And this statement follows from hypercontractivity of a different operator that's
Okay.
related to hypercontractivity in Gaussian space.
Okay.
Where is this orthogonal complement being taken?
In L2 of the SUN.
Okay.
Yes, we have like two proofs. One is with the heat kernel of the Laplace Beltrami operator, and it uses Bakri-Emery theory, and another proof is using a coupling to a better bound. That you use a coupling with Gaussian space.
And you know that's the right order of growth? The right hand side is
Yeah, so we actually can get D to the D, and this is sharp. This extra D to the D is needed, but I wanted it to be clear that it's monotone with D, so it's stated it later. Okay, so that's one theorem. So that tells you that the Fourier spectrum of a function on the special unitary group is also concentrated on the high degrees. And you also have the complementary thing that tells you that the high dimensional representations also corresponds to the high degrees.
Wait, I have an extremely stupid question. So, but this is getting smaller, is this becoming larger?
So that's why I studied it without the d to the d. So we have the slope to the d of 1 over alpha. So
Yes, but that's a constant, right?
it's not a constant. You think of alpha as very small. It's like e to the minus n or something.
Oh, I see. Okay.
And here you have to add an extra hypothesis that d is at most small constant times log 1 over alpha. So I wanted to simplify the statement.
Okay. No, it's.
Okay, so that's one thing, and then the other result is that the high dimensional representations they correspond to the high degrees. So yes, so there exists such that every sub-representation so every subspace of V equal to D that's invariant under multiplication from the left has dimension at least Tn plus T over D with the T. Okay, so it also behaves like the Boolean cube in the sense that in the Boolean cube, the dimension of the space V equal to D was n choose D. Only this thing. You get it in general, also in SUN. And then when you combine these two together, you get the improved bound, because basically, okay, so let's give you a proof sketch. Of the product mixing theorem. You can decompose your function to functions f, g, and h that are indicators of some sets, and the goal is to show that f convolution g in a product with h is close to the product with the expectations. The first thing that you do is you write f as the sum functions f equal to d, where f equal to d is the projection of f onto the space v equal to d. And the spaces v equal to d, they are not spaces that are not related to the group action. So the spaces v equal to d are invariant under the left action and also under the right action. And this gives you lots of nice properties. So what you get when you take this decomposition is that if you take f convolution g in a product with h minus the product of the expectations, you get that this thing is the sum of d from 1 to infinity of f equal to d convolution with G equal to D. Inner product with Age equal to D. So the case for D equal to 0, this is the product of the expectation. And because these spaces respect the action of the group, you get somehow the convolutions behave nicely, and you don't have any post terms when you take these inner products. Then it turns out that the Sarnak-Schwe lemma that tells you this, you can actually get that that if you take F equal to D, convolution with G equal to D, then the L2 norm of that is at most F equal to D2 norm times G equal to D2 norm divided by root of QD. Where QD is the minimal dimension of a sub-representation of V equal to D. Okay. And then once you have this thing, you have a lower bound on the dimension here, and you have an upper bound on each of these parts. You can combine these together to get what you look. So it's basically we combining the lower bound on QD with the upper bound on the projection. And basically, philosophically, the idea is that in SUN there are lots of bad representations, but they all correspond to low degree polynomials. And the level D inequalities tells you that all the Fourier spectrum is concentrated on the high degree polynomials, and therefore on the high dimensional representations, and therefore we don't really care about the low dimensional representations, and you can get much better bounds. Are there any questions?
So this theorem, is this just messing around with young tableau or something?
This lower bound, yeah. There are several ways that you can get it. There are explicit formulas for
This will cleanse all.
So the hook length is just for the symmetric group. Here there is a different formula, but the representations are indexed by young tableaus. That's the
Can you say anything about why you would expect this to give you the right bound all the way down to exponentially sparse? I mean, just that it happens to work out that it's all great. I mean, because you've got these conflicting scales, right? Like maybe low degree things, the saving isn't good enough.
So everything is sharp. Yeah. So this level D inequality is sharp for both, and basically they are sharp for product mixing, and so that's
Okay. But there's no easy way to say why you expect all of these bounds to be good enough, apart from that they are.
I mean, basically what you get is that right, you have here, if you look at this term, you have the product of the expectation. This appears at D equal to, then you look at D equal to 0, so, and then you look at D equal to 1, and you get the product of, you get something like F equal to 1, 2 norm, G equal to 1, 2 norm, Age equal to 1, 2 norm, divided by root n, because the dimension is n. So, and what you get here is that the 2 norm of F equal to 1 is very close to the expectation up to logarithmic factors. And these logarithmic factors are the things that's buttoning this root n, where you get such exponential bounds. wanted to say stuff about finite groups, but then 5 more minutes. So, or how many minutes do I have?
9 more minutes.
I can take it till the end. Okay.
Yeah.
Okay. Okay, so if you look at compact Lie groups, you see that there is exponential improvement of what you can get from quasi-randomness than what you can get by combining quasi-randomness with hypercontractivity. And for finite groups, it looks like there is an abstraction where you can't do anything. So that's a theorem of Feeder. And it uses the classification. So they show that if a finite group G as a representation of dimension D, then it has a subgroup of index quality. And we said that product mixing implies that if you take two random elements from large sets, the product is uniformly distributed, and that's obviously false for subgroups. So for finite groups, there are always these subgroups that have index that's polynomial in this quasi-randomness parameters. So there can't be any exponential improvement. But actually, it turns out that they are the only abstraction. And once you take functions that are uncorrelated with subgroups, then you can get better product mixing. Before stating so what we can show is the following. So okay, so suppose that is a non-alternating finite simple group, so finite simple group of Lie type. Then you can get a Bogoliubov type result. Then if you take A and A inverse times A, it takes coset of a subgroup of index over G to the O1. Sorry, of density. We get a polynomial Bogoliubov result that the density of the subgroup that A contains is polynomial in the density of A. Or the alternating finite simple group. Then and earlier we had a result about alternating groups. But, so a quasi-polynomial Bogoliubov. There is also a paper that's already on the archive. About SLN. And the proof is again based on level D inequalities. It turns out that only recently people working in representation theory like Guralnik, Larsen, and Tiet and also Gurevich and Howe they developed a level theory for characters. Basically, for every irreducible representation, they defined some notion of level, and they use this notion of level to upper bound the LP norms of the irreducible characters. And turns out that that hypercontractivity is a generalization of this fact when you don't care only about class functions, something for general functions. Basically, basically just stated roughly, I'll take the form if F is uncorrelated with subgroups. And you have this notion of level, so you find the space be equal to D. And the space of matrix coefficients. The space is spanned by matrix coefficients. Representations of level D. Then you have good upper bounds. The projection, the L2 norm of the projection of F to this space be equal to D.
I find level in general.
So one notion is a notion of tensor rank, where you take you have the permutation representation of every.
I see.
And then, not the same tensor rank that everyone here likes. Yeah, so I guess I'll stop here.